Welcome back to the channel. When we're using tools like Python, we can get really creative with how we activate and analyze our data. So I've demonstrated multiple times that we can use PCA for multivariate analysis with the added benefit of data visualization. But in this video, I want to demonstrate how we can take some of that information, generate some labels for the samples, and then build widgets to help us move through the large swaths of data for additional insights before we go through and begin building classified methods or redesigning the experiment. And so this is going to be demonstrated on the data we collected for the coffee adulteration video, the one before this, where we analyzed authentic coffee and commonly used coffee fillers, corn-based cereals, and other things. So here, I want to quickly refresh you on what we did in the last video. We used our common techniques such as SNV or Savitsky-Golay in some cases to perform signal processing on near IR data. I then quickly took that raw data file, passed it to this pipeline here where I'm selecting just the wavelength data. I'm applying SNV, and then I'm separating out my index values in this Y data series, and then I perform PCA. And that's where the video stopped. If we look at that output, we can see that we have what looks to be 4 different clusters, one over here, which I presume will be our authentic coffee samples, but I have not applied formal labels to this data yet. And then we have our 3 other commonly used adulterants, or at least in this case, simulated adulterants, pure corn-based cereals or other grain materials, whole grain materials that we're just using in this study. However, in this video, I want to demonstrate how we can use Kmeans to generate labels for this data, and then use Ipywidgets to make the data interactive, and perhaps try to begin figuring out which wavelength might be the best for analyzing this data. So while a device like this can collect several different wavelengths and produce thousands of variables, what if we only picked one? How could we do that? I'll show you how we could do that visually. And then in the video after this, I'll demonstrate which types of statistical tests we can use to do this mathematically. So let's do it. So I want to first generate labels using Kmeans. And since I estimate that we have 4 different clusters, at least that's what we can see visually, I'm going to instantiate this method with 4 clusters and my init as auto. And then we're going to fit the data on the scores data. So this data here is my scores data frame. And let me make sure I run all the cells, and I'll show you what scores looks like. And as you can see, we have our spectrum ID, which is the index of each of these data, and then our various principal components, which was generated from our PCA. I will fit and predict our instantiated model on the scores data, which will produce an array of clusters. Then we will create a new column in our data frame called clusters, and assign this there. And I'll just show you how we can use this to update our original scatter plot. And when we do that, you can see that we have 4 very reasonable clusters, which align quite nicely with our visual assessment of this data. So this is a nice gut check. So if there's cases where you want to explore new models, this is a good way to do that because it really makes sense with the type of data we want to build. Of course, there's many other methods we can use to develop clusters, but in this case, we're just going to focus on Kmeans. Next, I want to demonstrate how we can make this data interactive. And so what I want to first do is create a copy of my NIR data, and then I want to insert my clusters to that raw data. So NIR data looks like this here. And if I were to insert clusters into this data frame, I would update the data frame. And I don't want to do that because if I rerun the entire notebook, I don't want to have any issues with updating a variable that was run earlier. So to get around this, I use this copy method to create a copy of this and save that copy as this new variable called cluster NIR data. Then I use the insert method, insert my clusters into position 0, which would be the first column. It'll create a new column called clusters, and then we will pass in this array. And so now our data frame will look like this, where we have a new column called clusters added to our original data frame, but we've now updated that to cluster NIR data. When I do that, I decided to put everything in a single cell so that if you wanted to take a screenshot of this image, you could, but we have all of our methods needed to create an interactive workflow. So I'm going to be importing from Ipywidgets widgets and then also ipython.display, import display. And the first thing I want to do is create a list of my wavelengths. So this will allow me to create the slider that we can use to move through the data. And then next I create the slider, which we are using the widgets.float slider method. And I will pass in these respective arguments for the values in this method here, where we're going to instantiate our initial value for the first wavelength. And then we're going to set the min and max to be the wavelength range from the minimum value to the maximum value. And then the step size, because this can vary depending on the experiment, we're just going to set the step size to be wavelength at position 1 minus position 0. And because you know this is fixed across the entire study, this is a very appropriate way to set the step. Or we could just pass in 4, since I know the bandwidth of this instrument is 4. I'm going to pass the string wavelength to the description argument and then set the update to be continuous. If your computer perhaps runs a little bit slow or is low in memory, you could set this to false. Or if you just don't want to have it auto update the figure in real time, you can set this to false as well. Next, we create a function called plot box plot, where we'll pass in the wavelength. We're going to convert that wavelength to a string because that is the data type we have in our data frame. And then we're going to use the plt.figure to create our initial figure. And then we're going to add the box plot to that figure and then use our cluster NAR data, where X will equal the clusters column variable, and then Y will equal the wavelength as a string. And then, of course, we're just going to update the title and then render the plot. And importantly, we're going to use the widgets.interactive output, where we pass in this function, plot box plot, which is why we created this function in the first place. And we're going to assign this slider to the wavelength parameters, and then display the slider and the output. When we do this, you can see we now have what looks to be an ordinary box plot, where we have the values of each of our clusters at this respective wavelength, 1454. And as we slide this, because we set update equal to true, you can see that we have an updated plot. And this could be a really nice way, particularly if you add this to something like Streamlit, to make the data interactive and make it really easy to move through what will be thousands of variables one at a time, and very quickly to start building some insights into which variables might be very important. And so as you can see here, depending on where we land, some of the variables have a lot of overlap. So in this case, at 1966, there's a lot of overlap between cluster 0 and cluster 2. Cluster 3 is quite distinct, and cluster 1 is very tight and low. Thus, ideally, we'd be looking for wavelengths where the variability within the cluster is very small and the separation from the other means is very large. And so think about that as a hint as to which test we might use to figure out an optimal wavelength. However, visually, you can see that there are some features that look really nice, like this at 2302, where we have pretty decent separation, evidenced by the minimal overlap between the various boxes, and fairly tight clusters, with the exception of cluster 2, where we have these extreme values denoted by these diamonds here. Lastly, I want to show you what these clusters look like if we were to take our raw data, group by the clusters, compute the mean, transpose the data, and then create a line plot. And this is another way we could begin gathering some insights into which features, which wavelengths might be the best for separating out our data. For instance, if we look around 2054 and a little bit above, we would expect to see good separation between the orange cluster, cluster 1, and cluster 2 in green, and not much between the blue and the red clusters there. So let's look at that. In there, you can see we have a lot of overlap between blue and red, as we see here, and some separation between green and orange there. Now, this is perhaps still not the best way to do this. If you look in other regions, you can see that here, they're all overlapping quite substantially. If you come down and look at the raw data or the aggregated data, you can see what that looks like at this particular time. So with this information, we can determine visually which might be an optimal wavelength, or massive charge read this for mass spec data. But there are methods we can use, mathematical methods we can use to determine that, and I'll demonstrate that in the next video. If you want to see it, like, comment, subscribe, and I'll see you there. Peace.